Hi, good morning, everyone. This is Ali Rasek, and today is May 28th, Tuesday, and we are going to continue our course for about 1 hour and 20 minutes. I'm saying that we have already 25 people, which means that I can get started. Hopefully you hear me fine, and yeah, just it's very good time if there are concerns with everything that we are doing, from classes to recordings to whatever I put on your system, write a space, just raise your voice and unmute your mics, and we can fix it. And I forgot to say thank you to all the teams for submitting your work plan. I was just talking to Behnam, who is your like the teacher's assistant for this course, and he had looked at them overview, and he was happy. He said that all of them were like in okay shape. And as I previously said, this is only draft, and we will provide some comments. Looks like they will be minor comments because you guys have done a good job. We provide some minor comments so that you fix them and then send us the final work plan by the end of June 7. What I'm thinking is that by the end of weekend, I will also have time to quickly look at the work plans and give my comment or approve of Behnam comments. And therefore, next Monday, which is about late Sunday, or next Monday, which is June 3rd, I will make them visible, or I will ask Behnam to do that so that you see our comments. You will have a few days to apply those comments, which will be minor, and then submit the final work plan by June 7, as we have a deadline here. As we previously said, there is no class next Tuesday, so that gives even more time to apply the comments that we provided, or we will provide to you, and prepare a very nice final work plan. This is very important for your own good as well, so that you exactly know what you want to do. And also, you know how much time you need or how much time you asked for, and just spend that much time. I don't want you to do too much or too little. So just do enough, and everybody will be happy. All your team will be happy. I think we are in good shape. Behnam today told me that all look good, and I was happy. So looks like we are making this happen. I'm already looking forward to the presentation dates, 26 July and 2 August 2nd, when I will be at the class, and the teams will present, and we will all learn more. We will learn more than what we have during the class. There are 7 teams, so I will edit this slightly. Maybe second day, August 2, we will have only 3 presentations, and there will be randomized numbers. So I will choose randomized numbers as well, so that just because of your team number, you don't get preference. We want everybody to be equal in the class, like they have equal opportunity. That's what I believe in. Let me make sure everybody, yeah, so I don't need to allow anybody in. Sometimes I think the students come in with a different email address, and I have to just approve that they come in the class. Hold on a second. That one, admit. That's fine. Okay, that's my other phone. Sorry if something urgent comes up. That's fine. Anyways, we can continue. Good number of students. Thanks a lot. 27 strong. Yeah, you can say that. And Benham told me that you have chosen from these topics here. So I'm happy that I have given you enough options. Although, as I said, you could even find your own topic. Right now, we are continuing with module number 2, which is dynamics of structures for multiple degree of freedom systems. Meanwhile, so that you confirm them one more time that what we are learning here is valuable, I show you this. So maybe 1 hour ago, I opened this slideshow from the module number 1 that has this equation for assessing like log decrement method. That's the formal name for it, but that's a method for assessing the damping ratio for a system. Because I mean, I have a poor memory. I keep on forgetting whether 2 pi is on the nominator or denominator, etc. And so I was reviewing an analysis being done here at HDR. And so let me show you here. Sorry, it's too busy. This is done by my good colleagues and engineers at HDR. They are modeling a dam. I probably shouldn't say any further which dam is it or what we are doing. However, it's an earthquake analysis, and this is 1 block of the dam. I wanted to see, we have applied damping in different methods to the system, and there is dam and foundation and reservoir and whatever. So it's the main model is a lot bigger than the one that I'm showing here. However, I wanted just as a checker, as a person who overview, I wanted to make sure that they have gotten the damping right. So I did a free vibration test, and the system, as you see, is like from second 1 second is vibrating, but it's losing its energy. The energy is dissipated gradually. And so number 1, I was interested to see what is the main period of the structure. You see the vibration starts from 1 second. And yeah, I think maybe I didn't explain well. So I output the acceleration on this point on top of the dam. So all I did was outputting acceleration record on top of the dam after refrigeration, which means I slightly shaked this model of the dam and let it move. And then I outputted the acceleration there. I can show it again. That's the acceleration record for a few seconds. So that's the force that is pushing it, has caused some randomized acceleration. Then there is no force starting from 1 second, no forcing function. It goes back and forth. 1 complete cycle is okay. It finishes at 1.37 almost. So between 1 and 1.37, 1 cycle. My back of envelope calculation here on a sheet, just given the mass and the stiffness of the system, my period was also 0.37 seconds. So you can say here. So that's the kind of high-level check that we do on our models, so that they are not. Sometimes people call some modeling garbage in, garbage out. I mean, that's an extreme word. I never use it in real life, but sometimes it happens that it looks fancy, but the outcome doesn't make sense. So I do my back of envelope calculation here. I get 0.37 seconds There was one cycle finishing in 1.37 seconds. Then what I also do is that I look at the peak values of acceleration, multiple peak values. And I know that equation, but I don't have it on top of my memory. So it is a remote system. How can I get rid of it? No, that's your system. Yeah. Okay, I need another window here to, yeah, so I will close this if I can. So I will go back to that screen, but what I was saying was that I used that logarithmic decrement solution to also estimate the damping of the system, which was about 2.95%. Just by reading some numbers here, you see that I don't exactly read them. And yeah, so I was happy because I was expecting 3%. And if you work out these values in the equation for damping with free vibration, you will also see that they correspond to 3% damping. I'm using the negative values here, but the absolute value is important. So use the ratio of 0.37 to 0.313, and then use that equation that I should be able to get it. How can I get out of this? Okay, let me stop sharing and then share again. Yeah. I think Zoom doesn't make it easy for us. Stop sharing. Minimize this. Now share again. Right. So yeah, I had a bunch of windows on top of each other. I couldn't really manage them. Back to the story that I was telling was that I pulled out, like right now, my course notes are also my notes at work. So I don't need books anymore. I have created a good set of course notes for you guys and I use it myself. So I went back to this equation, log decrement method, and the values that I was reading to you were 0.378. Last time I read it myself on my notes, and 0.261 in 2 consequent cycles. And I use this equation for 2 cycles. When you have 2 cycles, then you divide it by another 2 because it's 2 cycles. Here it's written for 1 cycle between I and I plus 1. If it's between I and I plus 2, you have to divide it by 2 one more time. And I ended up with 3%. Bingo, I'm happy. I think our guys have done a good job, so I can approve of that. So what I'm telling you is that in the age of high-level computing and ChatGPT, etc., still you go to your class notes and use them to verify a solution, which is super important. Now, yeah, last time we went through this. Like this, and if it's bothering you guys. So we visited the multi-degree of freedom systems and high level explained that. Yeah, remember that there was a U total. I removed the total because it was not total anymore. So for you guys and also for future, for next year. So we went through all this and we discussed that we focus, although from like statics and analysis of structures, we are aware of many degrees of freedom in the system. We focus on the ones that are important to dynamic analysis and use some method, maybe static condensation, to get rid of the unwanted degrees of freedom. maybe when I was in college, when I was in university, the difference between, I don't know, 20 and 2 was very important, but maybe for right now, the difference between 2 million and 1 million is important to save the computational time. So it's important anyways. I don't generally appreciate it when people into analysis just think that we have unlimited resources. The level of resource and computation capacity is increasing, but the demand is increasing like twice as fast, and therefore we easily end up with, in a way, mathematical problems that we cannot solve because, say, maybe we get too ambitious and we want to run too huge a problem. Given our resources, like we have limited resources, the projects have limited budgets, and at this moment we have 24 cores, which again, there is some limits. It's not like unlimited. So in general, what I'm telling you is that your notes are important and try to at least have a high level understanding on them and practice a little bit, and they will be useful throughout your career. I think we stopped here last time and with examples. So we went through all that, and now we are going through the examples. 1 second. I should always quickly, sometimes I miss the chat, but now we can dig into the examples. Again, slope deflection relations. Yeah, I mean, a structural engineer should have them always in their back pocket, or maybe you just skip my slides for your professional life. It happens that you are worried that your computer simulation is wrong and you want to do a hand calculation. A slope deflection relation is a very useful tool. And generally for a unit rotation, we know what the reactions are and what are the moments. And also for a unit displacement, we can get the reactions in terms of shear force and end moments. And any movement can be imagined or decomposed into a combination of these movements. So theoretically, whatever shape a beam takes after deformation, you can, in a way, calculate the shear force and the end moments. Now we go to example number 1, which is equation of motion for 2 degrees of freedoms. In this structure, it's like your 2-story building, and so say the roof of the first story or the first floor, in a way, is twice as heavy as the ceiling, and normally ceilings are less heavy, and the flooring system is pretty rigid. So that's why we said we just assume that the stiffness of the flooring is infinite comparing to the columns. And the column stiffness comes from basically the bending. So when you talk about EI, it means that most of the stiffness that is considered is from bending, because normally the axial stiffness is much higher, and also the shear stiffness is much higher. So in combination, only bending stiffness matters. That's good simplistic assumption. So nowadays with computer capacity in SAP 2000, you just let the program decide about all that. You give it the area and ask the program to do as complex as possible, which is fine. But when you want to do a quick hand calculation, you should remember that the bending, the stiffness that is related to bending is the most important. Again, the columns on the first floor, like from base to the roof of the first floor have twice as stiffness as the second floor columns. Heights are the same, and yeah, masses I talked about. We are not concerned about damping, and all elements are axially rigid, which is, true. Normally the axial stiffness is a lot higher. Mass matrix and stiffness matrix is the question. Now, okay, so this is your first degree of freedom, U1, and then second degree of freedom, U2. So only deflection, lateral deflection is important. Mass at the first degree of freedom is 2m. Mass at the second degree of freedom is m. The stiffness of the first floor is 2 columns, and each one has, like, you probably can, again, if it's up to me, I will find it. I'm able to find it quickly from the books, or use this 12EI over L3 for the stiffness. It is practically stiffness when the structure moves laterally and there is no rotation at the ends. So there is no rotation here, no rotation here, only a unit deflection, which is identical to what we call a stiffness. That's for this bottom floor, and this is for the top floor. The factor 2 is because there are 2 columns in each floor. Mass matrix we created quickly, and a stiffness matrix. Yeah, so I didn't show this in detail, but basically what we have is for the first floor, so that you can do this exercise. I think maybe you know it from your analysis of a structure course. When you want to get this first term, what you imagine is that all the nodes are closed and only the first floor can move. And if the first floor moves by a unit, we have deflection both in this column and in this column. So the stiffness of both of them, both columns of first and second floor, they are contributing. So 24 EI over H3 here, but 1 time here and 2 times here, so 3 of them. And when you want to get the K22, you close this one, and only the second floor can move. And now the stiffness of the first floor is not really contributing, it's only the stiffness of the second floor. Therefore, you have the 1 factor here, only the stiffness from second floor is contributing. And similarly, of diagonal terms is, like, say, assuming that you have still closing this, and for a unit movement on top in the degree of freedom 2, you needed 24 EI over H pushed. Therefore, the reaction at the degree of freedom 1 is in the opposite direction. The same thing, opposite direction. That's where this number -1 comes in. And it's symmetric, so you don't need to do more. You just populate it symmetrically. Populating mass matrix is always a lot easier, especially if your mass is separated between degrees of freedom already. So you already have 2m in degree of freedom 1 and m in degree of freedom 2. And physically, mass cannot have off-diagonal terms. So mass matrix normally is diagonal, except that sometimes there are, like, we use math assumptions. Mathematically, maybe you assume there are off-diagonal terms, but physically, we cannot imagine that, like, there's only 1 mass in a degree of freedom. That's what at least engineering judgment is that. Okay, and now, so we write the equation of motion for when you have external load, varying load with time. Basically, mass multiplied by acceleration plus stiffness multiplied by displacement is the forcing function in time. And they said that there's no damping. So this is the complete equation of motion, as we called it in the title. Moving on, I think it's exactly the same picture. Yeah, so this is exactly the same U1 and U2. And we want to complete a modal analysis for these two, the same 2 degree of freedom system. Modal analysis means finding the period of the system. Period is like the top dynamic characteristic of a system. So we always are interested in finding out about the period of the system. Similarly, we simplified, called the K2 second floor to be K, and K1 of the first floor is twice as much. So we have the value, we previously have this value of the K1 and K2, and we know that K1 is twice as much as K2. We just are compacting the symbols. And same thing that we found out, diagonal mass matrix is here, and a symmetric stiffness matrix. So we always expect a stiffness matrix to be symmetric and mass matrix to be diagonal. There are exceptions, but normally, physically, or to the best of engineering judgment of a structural engineer, that's always the case. Like a stiffness matrix is symmetric, mass matrix is obviously symmetric, and also only diagonal. Now, if you remember this equation shown by determinant, that was supposed to help us find the frequencies of the system. So the determinant equation for a stiffness matrix and mass matrix of this, if you, I don't know, like I expect that you guys in 4th year know a tiny bit of matrix analysis and matrix analysis for static purposes at least. And determinant is also important, but you can just quickly ask your ChatGPT bot to refresh you on that and how to calculate the determinant of the matrix. This is basic matrix calculation. You just K multiply M by omega 2, and there are zeros here that I haven't shown, and K minus omega 2M, you create that matrix. And then you, as a refresher, even I don't have it on top of my mind, but I can Google search it or ChatGPT it and find how to calculate it. You will end up here. However, I'm able to validate, so that's very important for engineers because ChatGPT keeps on lying to me on a lot of stuff, but yeah, I can figure out which one is correct and which one is not. So you need good judgment. We're still in 2024, we still need good judgment. Just don't listen to the ChatGPT because yeah, I can tell you jokes and examples, but I keep on asking it questions and it gives me something, and then I say really, and then it says no, I made a mistake, etc. So like any of us, because I think it's high level trained on human language, and we humans sometimes lie in a way. So ChatGPT does the same thing. Keep your good judgment in interaction with people and also with ChatGPT. Yeah, so the story is that we have this equation. Don't get too worried about it. This is really a 2nd degree equation, and based on omega 2. So you have omega 2 to the power of 2 and omega 2 here. And yeah, again, I mean, for 20 years, I have been the greatest Google search user. Now I'm switching to ChatGPT. So again, I ask, oh, what is the solution for a second degree equation? It gives me the equation. I recognize that this is correct because I have been educated, and then I use it. And you use it, you get these two estimates of omega 1 and omega 2 frequencies, circular frequency, we call them. Circular frequencies of the system. And yeah, so you get the circular frequencies. You can get period from circular frequency, right? So because circular frequency is basically 2 pi, a full rotation around the circle, divided by period. So you can easily translate circular frequency to period. I have shown the mode here, so that the first mode is like for frequency. When you go in terms of frequency, the more important mode has the lowest frequency. As structural engineers, we normally talk in terms of period, and normally the most important mode has the highest period. It's true 99%. So at least, yeah, remember it for now. Maybe you will see some exceptions later on. And we will maybe I get a chance to explain more, or maybe not. But that's something to remember. Yeah, yes, there is no issue. Most important mode of the system has the highest period. Just remember that. That's one of the few things that I like you to remember. And again, we gave you, like, I think we described it last time, but maybe one time is not enough for students, for learners. So second time and third time, we can just repeat that. Determinant, use that determinant equation to get your periods. And then when you have the periods, you push it back, you put it back into your equation of motion. And now you can calculate the mode shapes, what we call the mode shapes related to each frequency. So this frequency is correlated with this mode shape. This frequency is correlated with this mode shape. And therefore, we have this first mode, the mode shape. What does the mode shape mean? Means like looks reverse, but really this is the first degree of freedom has moved by 1.2. Mode shape doesn't have a unit because it's scalable. It's like you can always, what it means is that the second floor moves twice as much as first floor. Therefore, there's no real unit to it. It might be inch or centimeters or kilometers, whatever. All the mode shape, what it tells us is that this mode shape is telling us that second floor moves twice as much as the first floor. And that's what you can say. You can see mode shapes in your SAP analysis as well. Second mode had a frequency, higher frequency, about 2 times as much. So the second mode has a frequency twice as much. And if you look at the mode shape, it is -1 and 1. So the first floor has moved in a way in a negative direction. Second floor has moved in positive direction. So again, as I said, mode shapes don't have units, and all they tell us is that they move the same amount in different directions. So yeah, I mean, maybe I should apologize. We do these things too quickly. Therefore, yeah, so if you learn high level and you can interpret SAP 2000 results, then you have done a great job. You have learned a lot. And yeah, going into these details, keep it as a reference, but you should be able to follow it. But I mean, this is a too quick course for being able to do it on your own. So, but it's good if you can follow and you can repeat in SAP 2000. You have done great for Civil 459 course that we have this term. Again, repeating the mode shapes and their corresponding frequencies. And now, if U0 is, this is part of the same example. Here we want to determine the free vibration response. If U0, 0 in parentheses means at the time 0. At the time 0, we pushed everything to about 1/2 and 1, very similar to first mode shape. This one practically has units, like as if we have moved it 1/2 an inch for the first floor and 1 inch second floor. And then we leave it so that it doesn't have any speed. So at the time equal to 0, we had some movement, but no velocity. And then we, in a way, remove our hand and let it vibrate on its own. Now, we know that the displacement of the system based on the mode shapes, we already found out that there should be according to the top equation here. So that's the equation for displacement. And if you do the first derivative, then you get the equation for velocity. So you know the equation for displacement and equation for velocity, but the only unknowns here, you have phi n, you have phi 1 and phi 2 already determined. However, you don't know about the a's. And because now you have 2 equations and practically 4 equations, and because it's at two levels. 4 equations, 4 unknowns, it could be resolved and get B1 and B2 is equal to 0, A1 is equal to 1, and A2 is equal to 0. So basically, anything related to the second mode is 0, and it's moving in the first mode. But it's not, not very unexpected, because the initial movement was in the first mode, and therefore the system will continue vibrating in the first mode. So we just excited the system in the first mode, and it continues moving in the first mode. There is no damping in the system, so it can move forever in the first mode. This cosine will remain the same forever, and the amplitude is there. So again, I know this is too fast, but I only expect you guys to just follow these things. That's as much as we can do high level for a 4th-year course in earthquake engineering, which covers a lot of stuff. So you guys are already very good. Now, we want to one more time review what we talked about Rayleigh damping, and try to assess the Rayleigh damping factors for a 3-story building. Here we have a 3-story building. These floors are heavier, so they are 200,000 kilograms, 200 tons each, and a 100-ton roof on top of everything. The stiffness, all the floors are identical. So all of them have a stiffness of 1,000 kilonewton per centimeters. Already the modal analysis is completed. your SAP 2000 in your favorite software, you have determined the primary frequencies of the system. I mean, the system is 3 degrees of freedom, so it has a total of 3 frequencies. The primary frequency, when they talk about primary, meaning the first one. Or if you say primary frequencies, we mean like 2 out of 3, because we will see and you will learn through experience that the modes with lower frequency have higher effect. So that's why we call them primary. We have found the mode shapes related to those 3 frequencies. And yeah, in a way, it's like 289 is for, I think it's for number 1, 500 for degree of freedom number 2, 577 is for number 3. As I said, shape functions, they don't have unit. So even if you multiply it by 1000, they are still shape functions. So it's only the relative movement which is important. So with the first frequency, which is about 11 hertz, which means, and this is the circular frequency of 11 hertz, which is like if I divide it by 6, means the frequency of about 2 hertz or less than 2 hertz. And then if I reverse it, it means a period of about 0.5, right? So at this moment, we are not concerned about that. All we know is that we have a period of about 0.5 seconds. And in that period, the primary period of the system, first floor, if the first floor moves by first floor is this one. So it's a little bit counterintuitive, but so that's the first floor. If the first floor moves by 0.29, the second floor will move by 0.5, which is less than twice. And then third floor moves more, so it has this shape. And then again, as you see, the second mode indicates reverse direction movement. So first floor has moved in negative direction, second floor 0, third floor in positive direction. Just an imagination of how the mode shapes are. And in your SAP 2000 or in your favorite structural software, just get these mode shapes, look at them first for the first period and second and third, and just get to get a high level sense. Now the system damping, we want it to be 5% for first and second mode. What is the Rayleigh damping? And so for the 11.5 and 31, we want it to be 5%. Calculate the Rayleigh damping, and then when you have the Rayleigh damping, what is the damping ratio for third mode? Again, we have the mass matrix, which is easy to assemble. The stiffness matrix is slightly more difficult. As I said, for the, like say, when you have a movement in the first floor and others are restrained, the stiffness of first and second floor contribute. So you have twice as much. And similarly for second floor, for third floor, if you have this one restrained and this one restrained, when the third floor is moving, it's only affected by one stiffener column, which is a stiffener. So that's why no surprise that we have a 1 here. And these are the reaction at the other floors when one floor moves. And it's symmetric, generally looks okay, looks healthy, we can proceed. 3 frequencies were already calculated for us. And when we were talking about Rayleigh damping, we said that how to calculate A0, which is mass proportional damping, and A1, which is a stiffness proportional damping. We had two equations for those. Omega I and omega j are the frequencies of interest, and we said that frequencies of interest for us are omega 1 and omega 2. They were inserted in there, and you get A0 and A1. So in a way, your Rayleigh damping is calibrated to first frequency and to the second frequency. And you can use the mass matrix, the stiffness matrix, A0 and A1 to assemble your, in a way, damping matrix. However, damping ratio is the most important to us. And so repeating the same thing, equation for damping ratio, this is set to be 5% for first mode and for the second mode. However, we should calculate the third mode, and then we can input this value into the damping ratio equation and calculate the damping ratio for third mode, which is about 6%. So the third mode is damped with a higher damping ratio. That's what we normally like in structural engineering. We want to, in a way, avoid any noise and nuisance. So we are happy to get rid of, we happily get rid of upper, I mean the upper modes are not supposed to have a lot of effects on the system, but upper mode means modes with higher frequency. But on the other hand, because of numerical errors, etc., they sometimes they mistakenly become important. We give them higher damping so that those mistakes don't happen. And we just get rid of them. We don't want them. We are only interested in important primary modes of vibration. Now we have one story. We previously discussed that. And so there's one story where I think we still have a rigid flooring system here. And this one story has like multiple, in a way, lateral load resisting systems, maybe shear walls. Maybe we can assume that there are like multiple shear walls in different directions. Or maybe it's bracing. It's not really mentioned. It's not important to us at this point. So we have a rigid flooring and say shear wall frame A in frame A and shear walls in frame B and frame C. So that the two directions have shear walls. But as you see for Y direction, you see Y in the Y direction, the shear walls are asymmetric, so we expect some rotation in the system. And the system should be analyzed and designed for that rotation. Now, like the B and the D are given for this one-story building. 48 tons sit on the roof, like the roofing system, and maybe also the other loads, the permanent, more permanent live loads and dead load. Normally we don't use live load in earthquake analysis, but we use estimates of permanent live loads. We will see that in NBCC, we follow NBCC. How to calculate the mass of the roof. Here we call it roof and it's one story, so it's like really dead load and maybe a bit of maybe 25% of snow load, maybe depending on the region. So nothing more to it. And stiffnesses are given in the two directions. 1100, the stiffness is provided by frame A, and frame B and C are 590 in in units of kilonewtons per meter. As you see, like the designer really intended to provide the same stiffness in both directions, like the structural designer, say almost 1100, 1200 in both directions, because the earthquake effect is practically the same each direction, and the mass is the same, then the earthquake effect is pretty much the same. So he or she, they are thinking about providing same stiffness in both directions, X and Y. However, there are some practical limitations and architectural limitations that prohibits putting more than one frame in the Y direction. So we only had frame A in Y direction with proper stiffness. And therefore, we have some rotational issues that we should design for. Eccentricity of frame A is 0.5 meter. Yeah, so that's already calculated for us. So frame A has an eccentricity of 0.5 meter in this system. While in the X direction, we don't really have eccentricity because it's pretty symmetric. So we want to do the modal analysis by hand calculation. When you do by hand calculation, you should be more observant so that you reduce the size of the problem that you are working on. But it's important because you always have to double check what your computer analysis gives you. Displacement in X direction causes reaction only in frame B and frame C. So when you have movement in X direction, this is very symmetric. So symmetrically, you only get reaction in frame B and frame C. And the center of mass, assuming that's in the middle, moves in the X direction, symmetrically divides between frame B and frame C. Therefore, for the X, we call it omega X. It's only, and we said that frequency directly is related to stiffness and reversely to mass. Two of them, both frame B and frame C, are active, 2 times 590. Mass was 48 tons. And we get a circular frequency of close to 5 radian per second. Yeah, so maybe I made a mistake when I was showing the previous slides. For circular frequency, we don't use hertz, we use radian per second. After dividing by 2 pi, then you get the frequency, which is in terms of hertz. Yeah, so all I wanted to check here is that the units are consistent. So 48 ton means 48,000 kilogram, and 590 kilonewton per meter means 590,000 Newton per meter. So the units are consistent. We can just directly insert it in there and get the frequency. And the mode shape is easy to imagine. Everything is moving together in the X direction. Now, Y direction, if we are looking at it here, it's more sophisticated. Force in Y direction causes both displacement and rotation. Hence, the stiffness matrix should be calculated. What happens is that we assume that we have a uniform roof and the center of mass is at the center, while center of stiffness is away. It has shown schematically, but I think we were given eccentricity of 0.5 that is used here. So it's like visually it looks further away, but it's only a schematic. It doesn't have dimension, and this E value is exaggerated, shown exaggerated way. It's only 0.5. Therefore, if we have to come up with the metrics. If we prevent any rotation and only move in y direction, obviously frame A is providing a stiffness. We already have the stiffness of frame A. If we only allow for rotation, which is this one, if we only allow the rotation, we previously went through this exercise, you can repeat it, and you can calculate the rotational stiffness, like the rotational part of the stiffness. How much stiffness is provided by frame A multiplied by the distance of frame A to the power of 2, and how much is provided by frame C multiplied by distance to the power of 2, also frame B. So you get this equation, and you can calculate the rotational stiffness of the system. Similarly, you can get the off-diagonal terms. Off-diagonal meaning that, say, if you, it's always symmetric, we said, so we can do one of the two. You can give it a displacement, the center of mass, you can give it a displacement in the y direction only, no rotation, and calculate how much resistance, rotational resistance you are seeing. And the rotational resistance that you are seeing is the stiffness of frame A multiplied by E. Calculated here, 550. So your stiffness matrix is populated. And here we have a new feature that you should be aware of again. Moment of mass, moment of inertia. Maybe you previously had seen that in your very elementary courses and you don't know what does it mean. But in dynamics, it has meaning. The moment of inertia of roof mass, meaning that integrating the distributed mass with respect to the center. And again, you can find it on Google or ChatGPT, etc. This is the equation for it. And so the unit is ton meter to the power of 2. Now the mass matrix is 48 tons. This is rotational, 832 ton meter to the power of 2. Off diagonal is 0. Going back to our equation of motion for free vibration, we have this equation. We have already assembled the mass matrix and the stiffness matrix, and we get the primary frequencies. Remember that number 1 was for displacement in y direction, and number 2 was rotation around the center. You even get the shape functions. Same thing. The first component is displacement, second component is rotation. So rotation also comes in sometimes. Frequencies and the shape functions. So this shape function says that if the first degree of freedom, which is y direction, moves negative, you have a positive rotation or reverse. So this shape function means that this roof system basically moves back and forth like this. Second shape function says that if you have a negative displacement, you also have negative rotation. So the second shape function is in a way reverse of the first shape function. And the frequencies are there. There was another frequency that we calculated, which complements these two. So we have a total of 3 frequencies. And Okay, maybe jumped. We can go back. So we have two frequencies here, and there was a previous one that we already calculated. This one, so 4.958 here for moving in X direction. And very, very close to that, 4.496 for Y direction and 5 for rotation. These are all radian per second. So we have the 3 periods and shape functions. Now the question arises, like we had 0.5 meter eccentricity. What if frame A has no eccentricity? And in that scenario, the 3 degrees of freedom are independent. So each of the degrees of freedom are independent, and as we are mainly concerned with displacements, we can only calculate the X direction that we already did and Y direction without eccentricity, which would be, again, very close to what we had for X direction. So X direction remained the same. Y direction, now it's a lot easier. Frame A is sitting exactly at the center, so there is no rotational effects for Y direction. You get the period for the Y direction movement as well. Rotational, if rotation happens as well, again, you already have the stiffness for rotational without eccentricity. I can go back there. I showed you the equation for that. This is it. So for rotational, when you have no eccentricity, that E goes away, and you only have this term, which gives you the stiffness, rotational stiffness. Because frame A is right at the center, so frame A cannot really provide any rotational stiffness. Frame B and C, they can provide rotational stiffness. And the off-diagonal terms, they become 0. When you have 0 off-diagonal, in terms of matrix analysis, means that degrees of freedom are independent, so they can be independently studied. Going back to the arguments here, we calculated the rotational frequency as well. So all of them appear to be on the very same order, very close to 5 radian per second. And they are independent, so they are independent from each other. 3 frequencies of the system independent from each other when frame A is right at the center. And so the X direction displacement was already independent. Y direction becomes independent if frame A is at the center. And again, independently, we will have rotations as well. They don't have interdependency. Okay, I tried to explain it well and quickly. Apologies for quick introduction to this topic. You guys will be very good at this when you get like 500 level course in dynamics of structures and go through quite a few exercises. But I thought that this is valuable to keep this in the course so that you have the high level concept. And as I said, like you go back sometimes when you do your analysis in your future life or your tests in grad school, then usually you can go back to this slideshow and validate your work. So that's as compact as it can get in 1 hour and 20 minutes, which is ridiculous, but we did that. Hopefully you learned something. Now, if there is no questions or discussions, I can give you a few minutes, then we can jump into the next slideshow. Let me peek into my messages. Maybe my colleagues are looking for me. Not really. Okay, that's okay. And let me jump into the next slideshow. I'm not seeing the comments. And I think I have the next one ready. Yeah, using SAP 2000 for what we said. So hopefully you at least have learned the terminology using there and the concepts, terminology. If you have learned that, then I feel very happy. But we had to work through those set of equations, and it's good that you have that slide showing your references. How we can do similar stuff in SAP 2000 software. I didn't double check with your IT. However, they were going to install a few instances of SAP 2000 in the computer lab. So if you don't have any other way to access the SAP 2000, there are a few instances there, and a few of you can go to the lab and computer lab and in a way try to learn SAP 2000 together. If you want to use it for, I have not yet really went high level look at your proposals. If the proposal was about using SAP 2000, definitely you can go to the lab and use it in the lab. However, I also realized that SAP 2000, I quickly went to their website. They say that their system is that the student version is not there anymore. So that's why UVic has issues providing licenses to everybody. But trial version, they have a trial version for 1 month. If you want to learn and use it for your project, even 1 month is good enough. Just plan it so that you maybe install it on your personal laptop at the start of the project and use it for 1 month. That should be plenty. Or maybe you already have like an old version, a student version already installed, which is different. I think, yeah, SAP 2000 keeps on coming back to me and everybody. It's such a nice software, maybe prepared by civil engineers, structural engineers. So it has the mindset of structural engineers. When a structural engineer uses the software, they can find their way through the software more easily. It comes to them more intuitively in a way. The people who are trained to be structural engineers. So it's not the most advanced software, but it's very good and practical and appreciated by structural engineers around the world. So I recommend that you spend some time learning it, and it's probably good for your job search, etc., to have that on your resume, saying that you have done one project, one simple example. Doesn't need to be earthquake. Like I have designed a structure for a snow load according to National Building Code of Canada using SAP 2000 software. I personally will look very highly about the person who has that experience. You guys have volunteered, no, I shouldn't say volunteer, but you have decided to take this course, which is a non-mandatory 4th-year course, which means that you are very interested in structural analysis, earthquake analysis, and this type of software. Okay, we get the introduction here, and then on Friday we go further. I think I copied this model here and I tested it to make sure that it's running and for everything. I probably have put it on your system as well, right side, but I will double check to make sure that it's in there. And whenever I'm uploading the video of today's class. So the model is already there. It's good for you guys to inspect a model which is already prepared and learn from a model that is already prepared by others. I don't even say it's prepared by me, it's by I modified it a lot last year, but it was prepared by previous teachers. But last year I just modified everything. Yes. Everybody's viewpoint is different. Every teacher, every engineer think differently. So I did plenty of modification based on what previous teachers of the course had provided. So basically, you have this model. We will do some test runs on this model. Finite element model, frame model. This is like a 5-story structure. So even more degrees of freedom than the 2 degree of freedom structure we studied through the examples. And so 5-story, and generally we even allow the nodes to move in, at least in the planar direction. We allow them to move and rotate in 3 directions. That would be 2 movements and 1 rotation. So this structure in general have a lot more than 5 degrees of freedom. And because the computer does the hard work for us, we are not too concerned about defining a few hundred or a few, like less than 100 degrees of freedom. Your computers at home and in the office are a lot more capable than that. As you see, the W sections are used for column and for the beams of the structure, and HSS is used for bracing. And the braces are like chevron, I think that's what we call them, chevron type, but concentric means that there is no, like we will see that when we do a steel design for earthquake. A lot of time we put them concentric, means that they meet each other, but sometimes we leave some spacing there, which helps with a lot more energy dissipation and ductility, which is very important to a steel design and generally earthquake design. That's the structure that you have. Back to the slideshow here. I have tried to, and double emphasize or emphasize one more time the section property, W section, or sometimes we call it I section because resembles the letter I of the alphabet. So this W section is for beam or column, typically defined in sub 2000. HSS section typically defined in sub 2000. And when you become more fluent with using sub 2000, you can use the databases there. A lot of the information in the manual of steel construction in Canada or the similar one in the US are accessible in sub 2000. And I believe there are lots of European codes and Japanese and others are accessible. The most important for us is Canadian and US profiles are in there. So you just go to the database and add it, and all the section properties come in easily based on the name. Let me make sure I'm not missing chat in the last few minutes. Okay, so we have these section properties we already discussed, and then they're also dependent on material properties, which you can choose here. In Canada, we use a steel with yielding of 350 megapascal. which corresponds to about 50 KSI, so plus minus 350 megapascal. The ratio is very close to 6.9. So in engineering, you should sometimes remember some of those golden numbers because like here in Canada, also in the US, we switch a lot between metric and imperial. So one of the golden numbers is 6.9 between PSI and megapascal. And another one is like inches 2.54. So you don't want to memorize everything, but these things repeat so many times, especially like a person like me. I switch a lot between Canadian projects and US projects. So, and in Canadian projects, you need imperial as well. So I recommend that be comfortable with that. So it sounds weird, but it's not too difficult to jump between the two systems. Basically, so the assignments, when I receive a model prepared by others or junior engineers, sub 2000 allows you to just right click and see some of the properties at each node. So quick way of checking and even modifying. We have restrained anything out of plane for all the nodes because we are only interested in X direction pretty much and in plane. So we U2 Y direction is out of plane. We have restrained it. Rotations around axis 1 and axis 3 are out of plane. So we have restrained them because we don't want, number one is computer time, which we said is not super important now, but number two is that we don't want unwarranted modes of vibration, etc., that we are not even interested in them. We don't even provide support in the Y direction. So we restrain it, we are not interested in them. And masses applied to each joint are also shown here. But yeah, we will discuss further about this model. This is the most important, one of the most important things. You learn this term, how to use SAP 2000 and similar software for dynamic analysis. Yeah, exactly 12:20. It's about time that, yeah, you guys enjoy the rest of the day. I will be here for a few more seconds in a way, as I'm not seeing any questions. Yeah, have a good day. Bye. You are okay to go. If there are no questions, I will submit in about 1 minute. Nothing. Okay, have a good day and bye.